Welcome back to day 6, Transformations 2. And what we're going to do is extend what we were working on in the very last lesson. In the last lesson, we worked with the C and the D numbers, and we found that they were shifts. We had the horizontal shift and we had the vertical shift. And I called this C the pre-op number. Remember that? And that was because that happened before the function was operated. That's why I'm calling it pre-op. And because it happened before the function, you moved opposite of the sign that you might think. And then the D number, I said, since he's happening after the function is operated, he is your post-op number and he's going to affect it exactly as you think. Meaning, if you see a +3 for a D value, it's going to move it up the rate. And so then today we want to look at the other 2 transformations and see what they're going to do to our graphs. Now remember, please, that we always start out with our parent function. So you're going to want to, if you haven't already looked carefully at these, you're going to want to look carefully at these parent functions. We've got our constant function, our identity function. They're pretty easy, guys. V. That absolute value guy, we see him a lot, so make sure you get comfy with the absolute value. And then we've got our quadratic function there. And you know, you can actually extend that quadratic function idea. Remember that at the very end, we talked about power functions, where if that a is any even integer, or even whole number, I should say, he's going to look like this. Okay? He's going to kind of look like a parabola. There are some differences, but that's real helpful to you. Okay? Well, we have our square root. Now remember that that square root, he's just formed how? He's just like half of a parabola that's turned sideways. Okay. We've got the cubic function over here, and after our last lesson, you realize, oh yeah, if this exponent is any odd whole number, well then they all kind of look like that. Okay, so you can make that note and then kind of have it in your library of functions. And then we have our cube root, which is just that last guy reflected, and our sine curve. Now remember, you do not have to be able to graph sine curves. All you have to do is kind of go with me now, be comfortable with them, just as we play with the values, because we can kind of see some things in the sine curve we have trouble seeing on some of the others. And remember, if you haven't used twin plot, you don't have another graphing utensil, might be helpful to you. Okay, the first thing that we're supposed to graph today is essentially y equals 2 times sine x. Well, the last guys were all added or subtracted. So this guy's different because that 2 is being multiplied onto the sine function. And then you have to kind of think, well, is he happening pre-op or post-op? Well, in fact, let's go ahead and go over to our exploration. I like to explore here within our sketch pad. And I've written the equation down here with both of our parameters. We have an A parameter and we have a B parameter. And you'll notice that while the C and the D guys were added the last time, now I know you say, wait a minute, she's nuts. That C was subtracted. Isn't subtract just add opposite? Okay, so the C and D parameters, they're added on, and the A and B parameters, they're multiplied on. And I want you to try to distinguish between which one of these guys was the pre-op and which guy is the post-op. Now, how do you know? Your algebra training tells you that. You know from order of operations that I have to do inside that parenthesis first. So whatever that B value is, I have to multiply him before I operate the function. And then after I operate the function, I multiply times this. Okay, so what we want to do is explore what happens. So look at our basic graph. And remember, I have my numbers up there. And of course, we have to kind of approximate a little bit. So A is just a little bit more than 1 right now. And what I want to do is grab a hold of this. And while I'm pulling it up, I do want you to notice that those A values are getting very small over there. Look at that. A is 0.39. What's happening to the graph? Let me see if I can grab some more of it. It keeps getting smaller and smaller and smaller and kind of flattening out. Well, what happens if I make it bigger? Oh my goodness, look at what it's doing. Do you realize that this is essentially vertical stretch? And I want you to focus in on something. And sometimes I use a slinky to show the idea of we're taking this curve, this sine curve, and we're stretching him. Well, you know, if you stretch something, you kind of have to have a point of reference or a line of reference from which you're stretching. So here's what I want you to do. Let me see if I can get my A back close to 1. If it'll let me play with my A value and get that close to 1. Okay. There he's kind of close to 1. Now I want you to focus in on a couple of things. I'm crossing the x-axis at the origin, then I'm crossing here a little bit past 3, okay? And I'm crossing over here at about 6.5 or so, okay? And then I want you to watch what's happening here as we stretch this guy. Notice that those points on the y-axis, they're staying, or the x-axis, they're staying right on that x-axis. And what's happening is all the other y values are getting stretched. And then if my A value is less than 1, look at what it did. It essentially scrunched it. Instead of scrunch, we might say compressed. So if my A value is less than 1, here's what we've basically been able to discover here. If I have f of x is equal to a times some other function, I'm sorry if you don't like this, maybe instead of f of x I can call this y. It might make you less scared of what you see. If I am multiplying this guy, he is my vertical stretch. If he's bigger than 1, he's actually making it grow bigger. You know, that kind of makes sense. You're multiplying by something and it's making it bigger. And if he's less than 1, he's kind of scrunching it down. Now, let's see if this will behave. And if this behaves, big question would be, so what if he goes negative? What if my A value is negative? Do you have a guess before we take a look? Remember, I'm multiplying afterwards. Well, let's see what happens here. Did you see what it did? Watch again. There A is positive. A is negative. Might be a little bit hard to see. We'll see it again on some other functions. Essentially, it just flipped it. Why would it flip it? Well, you know, if you did have a value of positive 1 and then you're going to multiply it by a negative value, isn't that going to throw it down into the negative territory? Yeah. And if it had been a negative value, you multiply the answer times, the y is the answer, you multiply that y value times the negative number, it's going to shoot it up there into positive territory. So that kind of makes sense. Okay, well, while we're playing with this sine function, and here's the biggest reason why I grabbed the sine function, along with the A value, the B is really cool. Let's see what this B does, if I can get him to behave for me. Oh my goodness. Kind of looks like a spring or a slinky, doesn't it? Look at what this B is doing. Two things I want you to be thinking about. First off, how would you describe what's happening to the graph here? And as B gets small, what happens? And as B gets bigger, what happens? And then the last thing I want you to kind of pay attention to as I keep playing is where is it anchored? Where is that spot from which it's moving? Do you realize it's doing this? It's doing a horizontal stretch and compression. Now, in all honesty, that's a little bit hard for us to sometimes deal with these B numbers, and so we're not going to do a whole lot of work with the B number, but I do want you to know that that's going to be your horizontal stretch or compression. And what happens when B is bigger than 1? Look at what it's doing. Well, actually, B is smaller than 1 there. When B is smaller than 1, it's stretching that guy. When B is when B is bigger than 1, it's compressing it. Now, doesn't that seem to be opposite of what you think? When B is bigger than 1, it compressed. When B was smaller than 1, it stretched. But now B is a pre-op number, right? See, when you're doing these operations ahead of time, they start behaving a little differently. And remember, I told you, you might want to try playing with the table of values if you want to get a really good feel for why that is doing that. Okay? Well, let's look at another function. We've got our old buddy, the parabola, and you know what a basic parabola looks like, right? Now, we've got an A value right now of 1.17, so essentially it's our basic parabola, and I'm going to see if I can change my A value. And looky there. Now pay attention, even though my finger is going up, the A is getting smaller. Now look at what it's doing. The A is smaller, 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 smaller. They're all smaller than 1, and then the A goes back to 1. And now the A gets bigger than 1. Well, you know, you guys probably studied this when you were in, say, either Algebra 1 or Algebra 2. And a lot of times you were told on an equation like this, for a parabola. Do you remember ever seeing this guy before? A lot of times teachers will say what that A does is that A closes it up, or it opens it up. Well, technically not. What the A does is it stretches it. But in the process of stretching it up, because see, right now I'm stretching that A up. Let me see if I can make it stretch a little bit more. Okay? But look at what happens. As it stretches up, it looks like it's closing. And when it compresses down, it's not really opening up, but it looks like it is. Because you have less vertical space to reach that particular value, and so it looks like it opened. But the A value is my vertical stretch or compression. Okay, so what's the B going to do? Oh, hang on, before I do that, if this will behave anymore, let's see if I can make my A value go negative. Now watch. Oh, there's a negative 0.08, so it's a small value except it's negative. And look at what's happening. It's still doing the stretch idea, but the negative will flip it over the x-axis. Now, I always like for you to think about, well, why would that happen? And just like we talked about with the sine curve, the fact is that right now I have all these positive y values. If I multiply those by a negative a value, that's what flips it down. Okay, well, let's stop with the A for a minute and let's see what the B can tell us. Let's see if I can grab a hold of B and get him to move for me. Okay, there's B and he's getting bigger and bigger and bigger. Now, it might look like he's being stretched, but remember what he did before with the sine curve? And that's really one of the reasons why we have to look at several of these. When we saw him on the sine curve, he did this. He was a horizontal stretch and compression. Now, can you visualize this as I move it again? That what's really happening on this parabola is that he's doing this. Now, because of the features of a parabola, it's a little bit hard to distinguish between the vertical stretch compression and the horizontal stretch and compression. But there it's actually being compressed in when B is bigger than 1, and it's being stretched out when b is less than 1, doing that opposite thing. Okay, well, let's look at our square root. I didn't do the negative b there because you'd have trouble seeing it, but you're going to like what you see here. Okay, so now my parent function is the square root, so we see that half of a parabola going there. Now, what do we expect the a to be doing? The a should be a vertical stretch or compression. Now, where is the anchor for the a? And this is really important, and especially if you go on and you have to graph trig functions with these transformations, then the anchor is extremely important. For the vertical stretch or compression, you're anchored at the x-axis. So you're going to compress in towards the x-axis or stretch away from the x-axis. All right, let's grab the a and see if he can move on me. There, a is getting bigger. Does it look like a vertical stretch? Yeah. And a is getting smaller. Does it look like a vertical compression towards the x-axis? Now watch, he's going to go negative. Flipped right over that axis, right? And you know, as a becomes like we're at negative, just about to -2, that did a vertical stretch away from the axis, but because it was negative, he flipped him down as well. Okay, well, just to make us all feel better, we'll put him back up where he kind of belongs, if he does. Now let's look at the b. Now remember, the b is this, okay? So let's watch what happens as we try to move b. In this case, b is getting bigger, which actually means he's being compressed in towards the axis. Well, when I say in towards the axis, in the case of the horizontal, and I don't think we might have made that point back on the sine curve, the horizontal compression or stretch is all relative to the y-axis. Okay? So, right here, as I make this y value bigger, he is compressing in towards the y-axis. And if I make it a little bit smaller, he's actually stretching away. I know that's a little bit hard to see, but watch here. This is what's really cool about the b. Watch what happens, this is the first time you've seen it, that we've talked about it, when b goes negative. Why did it come over here? What the heck? But you see, here's why. I don't want to deal with a negative 0.17, so what if I say y equals the square root of negative 1 times x? Well, first off, with just the parent function, what's the domain? What numbers can I put in? Remember that crazy video about putting in? Yeah. Okay, well, I can only put 0 and positive numbers in here. Agreed. Now, if I put this negative sign on the inside, that's a pre-op number. It's a pre-op multiplication. And so it's saying you're going to first change that puppy sign, then use square root, which means well, you can't put positive numbers in anymore. You can only put negative numbers in. Well, that's kind of cool. Because here's basically what you get figured out. Your b number is your horizontal compression or stretch. And by the way, this all goes together really nicely. b is a pre-op number, so he kind of works opposite of what you think because he's on the inside before you operate the function. Now, he's anchored at the y-axis, the center of the universe, according to René Descartes, right? Okay, so we've got it coming in here or stretching out. And if b is negative, we're going to flip it over. What else? The y-axis. It all makes sense together. Now, in case of the a number, he's my vertical stretch compression. He's a post-op number. He's happening after the function, and so he is exactly what we would anticipate. With a big number, he's going to stretch. Small number, he's going to compress. Where is his anchor? X-axis. Makes sense. Now, if a is negative, what's he going to do? Flip over the x-axis. Okay, this is really cool that you can put all this stuff together and come up with some pretty complicated graphs. Okay, our crazy little goofy graph. The question is, what about the graph of y equals 2 times this if this is the parent function? Okay. Now, is that 2 an A number, a B number, a C number, a D number? Well, first off, the fact that he's multiplied on means that he's an A number or a B number. Okay, those are the two that are multiplied on. And the fact that he's happening after the function is operated means he's post-op, he's an A number. Okay, so what does the A do? He's a vertical stretch. Where is he anchored? The x-axis. So you know what? If I need to do a stretch on this guy right now, here's what I'm going to do. I'm going to start by going right to the x-axis. That puppy is staying put, and that puppy is staying put. They are anchored down there. Why? Really easy reason. What are the f values, the function values at those 2 points? Well, it's 0. What's 2 times 0? Still 0. Okay, now all I need to do is go to the points that I know. Like this guy is currently sitting at -5, 1. Now on a vertical stretch, he's not moving horizontally at all. He is simply stretching away from the x-axis. So the x-coordinate doesn't change. But this y-coordinate, that's the f of x, it's going to get multiplied by 2. So I'm going to go to -5, 2, boom. There's where that point ended up under this transformation. Now this point is currently sitting at, and I know you might have trouble seeing those little points, he's at -6, 3. Now remember, that x value is unaffected, but the y value is going to get doubled. So he's going to go to -6, 6. Boom. So I can draw this part of the graph. I know that I go up to there, and then I go up through that point. Now let's continue down here. This point is currently sitting at 4, -2. So under the transformation of a vertical stretch of 2, he's going to go to 4, -4. Hey, by the way, do you see that he's twice as far away from the axis? Try to put these ideas together because I think they're so beautiful. And then there's one little point, if you can see it. He's sitting at, what, 5, 6, 7, 1. He's right here. And he would end up going to 2. So he goes to 7, 2. And we go, boom. Now that looks kind of whacked out there. But if you look really carefully, do you see that essentially what we've done is taken that, and it's kind of a distortion, but it's stretched away from the x-axis. He's down twice as far as he used to be. He's up twice as far as he used to be. And he's still anchored on the x-axis. Okay? Well, because I'd like to use this same graph, I'm going to erase this, and then we'll take a look at the second one that I put down, just because this graph is kind of busy at this moment. Okay. Now, my last graph there is y equals f of -x. Now, that's not just an f of x. There is a parameter in there. You know that there is a 1, even though you don't see that 1. So we've got -1, and that's, first off, a multiplied parameter, which means it's a or b. And he's pre-op, which means he's b. And what does the b do? It's this guy. It's all about your horizontal stretch or compression and flips. And I will tell you that in this particular course, a lot of times we focus primarily just on that flip. So this guy's going to flip. Now keep in mind, the horizontal stretch compression, that's all in relation to the y-axis. So what's the negative going to flip me over? The y-axis. Okay, so let's see how that would work. First off, any point that was on the y-axis is going to stay there. Because if I flip over the y-axis, you're still there. All right. Now, if I have this point, which is sitting at 4, -2, and I want to reflect him over the y-axis, do you know where he'll end up? Instead of being 4 to the right, won't he go 4 to the left? And he'll be sitting at -4, -2. Okay. This point is currently sitting at -5, 1. So he's 5 to the left. If I flip him over that axis, he's going to go 5 to the right, and there he goes. Okay, so right now I have that one side flipping to there. Now this point is sitting at -6, 3, so he's going to go to +6, 3. And really, I can just move this one more point. This point is sitting at 7, 1. So he's 7 right, up 1. So I'm going to go 7 to the left. And up 1. And boom. That's pretty cool looking. Don't you see that flip? Well, yeah, it's not perfect, but okay, be nice. All right, well, let's go ahead and leave these guys for the moment and go back to the PowerPoint. So if I see this particular equation, what have we learned from playing over there with Sketchpad? Well, we've got 2 times. Now that is an A or a B because it's multiplication. Because he's happening after the function, post-op, he is the A number. And the A number is all about vertical shift. Okay? So here's what I do. Remember, anchor, anchor, anchor. So I could go ahead and put those anchors in right now. I could say I've got the origin, I've got this point that's about a little past 3, and then I've got this other point that's a little past 6. Okay, same thing on the negative side. Okay. Now, instead of hitting 1, what am I going to hit? What's my stretch factor? My stretch factor is 2. I'm going to take 2 times all the answers. And you know what? Remember I told you back on the first lesson that sometimes we just don't pay attention to as much information as the graph really shows us? This point is about 1.5, 1. Now this is the answer coming out of that function. So if I double him, it's going to 1.5, 2. And this guy is at around 4.6 maybe. And he's at -1. Now again, the input is not touched at all, and the x-coordinate is your input. It's this that's going to be touched, and he's going to be multiplied by a factor of 2. This is a multiplication. So he's going to go to a -2. And by the way, you could do this on the other side as well, but what you get is this beautiful stretch of 2. Hey, by the way, when you get into trig class, if you get into trig class, we call that amplitude. Okay? Kind of cool. All right. Well, -2 sine x. What is this 2? See the A, the B, he's the A, right? Now we know what the 2 does. The 2 stretches it. What does the negative do? Flips them. Okay? So let's take the anchors. Remember, in the case of a vertical stretch or compression, you're anchored on the x-axis. So I can go in there and put my x-axis points in there from the very beginning. And I'm just putting a rough estimate on there. Now, the fact that this is negative is going to flip him over the x, right? And you know what? You really don't have to memorize that. Exactly the same reasoning that I was just using. If this is 1.5 comma 1, you're not touching the x-coordinate. That's the input. You're going to take the output times negative 2. It's going to take it to negative 2. And that's what forces this guy to be flipped. Okay? And again, it's not a beautiful graph, but that's the rough idea of what he's going to do. Okay, this is fun. What about a 1/2? Now, by the way, that still is an A number, right? Good gracious, we're getting a lot of A numbers. We still are anchored at the axis. And the only thing different now is we're going to have just half of our vertical growth, so to speak. And he's going to kind of look like this. Yeah? Kind of like a half pint? Huh. Okay. Oh, here he's different. Sign of 2x. You know, you say, well, we had a 2 here just a minute ago multiplied on. Oh, but this is a big difference because the 2 is on the input. That's a pre-op number, okay? Now, I'm not going to graph him because I'm not going to make you guys do that at this point in time, but that's going to be a B number, which does what to the graph? It's this, right? Horizontal stretch or compression. And he does opposite, so he's really going to stretch him. But there's no reason to put you through it just yet. We'll get it at another time. Okay? And we'll get rid of those guys too. So essentially, what did we learn? Let's put these guys all together. A is going to affect your vertical stretch or compression. If A is bigger than 1, remember, he's post-op, so he goes according to what you think. If you've got a multiplier of 3, you think, whew, it's going to make it bigger. Multiplier of 1/3, you think it's going to make it smaller. And it does on the A value, because he's the post-op number. Now, in the case of the B, he's the horizontal. And because he's a pre-op number, he actually goes opposite of what you'd think. The only thing you're really going to need as far as the B is concerned is if that B is a negative value, it's going to flip it over that x-axis. Because with a lot of the functions that you guys are looking at, it's going to be really hard to see the effect of that horizontal stretch or compression anyhow, okay? And then it does become really important in our trig graphs, but you guys won't have to do trig graphs in this particular course. All right, so now we're going to move away from sine, and that was just for us to do some playing. Now comes what you got to do. So we take a peek at that guy and it says 3 absolute value of x. And you say, well, if I ignore the numbers in the problem, my parent graph would be y equals absolute value of x. And I know what that guy looks like. He's that v that goes through 1, 1, negative 1, 1, and 0, 0. So then you got to look at the 3. Is that 3 an A number, a B number, a C number, a D number? Your first thought is, well, how is he attached? He's attached on there with multiplication. That makes him either A or B. Okay. Is he being multiplied on before the absolute value operation is happening? No. He's being multiplied on afterwards. That makes him post-op, makes him an A. What does the A do? Vertical stretch. What's your anchor on the vertical stretch? the x-axis. You're going to stretch away from or towards, you're going to compress towards the x-axis. So that means this point, 0, 0, is going to stay put. It also means that this point that's sitting at 1, 1, he's going to get stretched. Where's he going to go? You're going to take that y coordinate and you're going to multiply it by 3. So he's going to go to 1, 3. This guy is negative 1, 1. Where's he going to go? You're going to take that y coordinate, multiply him by 3, boom. Now, does that graph look like I took this guy and stretched him? Works for me. Okay. Parent graph, quadratic, which means that when we graph him, he looks like our buddy the parabola, right? And some handy points are we go through the origin, we go through the point 1, 1. You know, it's really funny how many of these parent graphs go through 1, 1. And we have negative 1, 1. Okay. Now, do you actually see a parameter there? You don't see a number, but you have to consciously think, oh, wait a minute, that's a negative 1 times an x squared. So that negative 1 is happening after the squaring. And you say, how do you know that? Order of operations. You know, you thought that was such a piece of cake and such a goofy little thing. Oh, it's pretty important to us. So order of operations says you'd have to do that squaring first and then the multiplication times the negative 1. So he's your A number. Now, the fact that it's a 1 means that you're not really going to visually see a stretch, but that negative is going to do what? Flip him. And again, think about this. You were getting a 1 out. That multiplies the answer times negative 1. So he goes to negative 1. You got a 1 out over here. Gives you a negative 1. And there you go. So that negative, because he was an A value, just took that graph and flipped him down. Yeah? Cube root. Cube root. Well, you might have to sit there and flip back and see, what does that cube root guy look like? Well, here's what a cube root graph looks like. He goes through, guess what, the origin. He goes through 1, 1. He goes through negative 1, 1. You want to just connect those dots? No. But we've got this real nice S curve that goes up through those points. Yay. Now, what am I supposed to do with that S curve? Well, let's take a look. That's a negative 1, and that's a negative 1 that's multiplied on. And he's multiplied on the inside because, again, think of order of operations. Essentially, that's a negative 1 times x, and then that answer is being cube rooted. So that's a B value. Now remember, B is this, horizontal stretch and compression, anchored on the y-axis. With a negative, it flips it. So that point, 1, 1, where's he going? 1, negative 1. This guy's staying put. Hey, anybody on the y-axis is staying put because when you flip it around the y-axis, they don't have anywhere to go. And this point, negative 1, is going over to here. And so we have the backwards S. That's actually pretty cool. I mean, look at this. This guy flipped around that y-axis, and there's what he looks like. Remember, if you get that and you're thinking, did I really do that right? What could you do? Remember, if you got a punt, sometimes we've got to in life, make a table of values and kind of check some things out, okay? Make yourself comfortable. Well, you wipe away that 1/2, and my parent graph is y equals x cubed. So we know y equals x cubed goes through these 3 great points, but he's kind of an S in another way. What's that 1/2? Is he A, B? He's not C or D, because those are added. Those are added. Is he happening before the cube or after the cube? He's happening after the cube, so he's the A value, and so that is vertical stretch or compression. Now, on the A, does that go like we expect it to go, or does it go opposite? You know, there's a lot to keep straight, but once you get this all down, I think you're going to love it, because then we just change the function, but everything else about that parameter stuff stays the same. The A value goes according to what you would expect. So with a multiplier of 1/2, I would expect it to scrunch it, compress it, and that's what it does. Remember, you're anchored on the x-axis so that 0, 0 stays, and this point 1, 1, you're only affecting the output. That output is being multiplied by 1/2, so he goes to there. And this point, you see, you always want to have a few points that you can kind of play with. That -1, -1, well, he's going to go to -1, -1/2. And then I ask you to just kind of curve it through there. It's a little bit hard to see, but can you kind of see how that kind of sunk in towards that axis? Kind of got compressed in there? Yeah. Okay, that's kind of cool. Okay, now I'm pulling a twist on you. The nice thing is I'm warning you ahead of time. Take a look at what we've got. If you strip away the parameters in this, get rid of the 2, get rid of the 3, you see that my parent graph is y equals square root of x. Now we know what that guy looks like. He goes through 0, 0, 1, 1, and boom. Now, is that 2 an A, a B, a C, or D? Well, he's the A. He's being multiplied after the operation. He's a post-op number. So A equals positive 2. Kind of make note of that. Now that 3, is that, well, it's not an A or a B. They're multiplied on. This guy is being added on. So he's either a C or D. Now that's that last lesson. Ugh. Okay, so if you remember, the C was the pre-op number and the D was the post-op number. And in this case, after the square root is done, we double and then add 3. Man, that guy's like the last thing in the world to be done. He's a D number. Okay, so what does the A do? What does the D do? Shifts the whole thing up. Now, by the way, they're both vertical moves, but please keep straight the difference. One of them is a vertical stretch in which the curve is actually changed, and the other one is a vertical shift in which you just peel it all up and just move it. Okay? So here's what I suggest we do. First, do the stretch. I'm going to start at 0, 0. And I'm going to stretch that up to a 2. Now, because this is just my first one, it's not my final one, I'm going to kind of do a dotted. Kind of looks like that. Stretched them up. Good. Now, I need to handle the D of a +3. And that says shift it all up 3. So this guy's going to go 1, 2, 3 up. This guy's going to go 1, 2, 3 up. And here is my final graph. Okay? Hey, do make sure if you're doing several graphs on one that you label your final graph. Okay? Now, this is pretty small print. I realize that, but you actually have all of this information. I just kind of put it all together because I wanted you to see this big old equation, because that was our ultimate goal. with any particular function, because that f function could be absolute value, he could be square root, he could be x squared, he could be a sine curve, he could be a log curve, he could, lots of them. But whatever that function happens to be, there are 4 different parameters. And I want you to notice that a and b are multipliers. C and D are added, subtracted. B and C are pre-op. A and D are post-op. Put all this stuff together into a nice nutshell, and maybe you just need to kind of write some of your own notes to keep it all together. Because as I said, I know it's a lot of information right now, but it's so beautiful because it is consistent as we change functions. Okay? Now, since you got 4 of them, you might say, well, in what order do I do these? The cool thing is, you can go alphabetical. So you can do A and then B and then C and D. Ultimately, I would say this. These 2 guys, these are your shifts. So you can do them last because it's pretty easy after you've done your stretches or flips, then slide it to where the final resting place, so to speak, happens to be. Now, the A and the B being the stretches, you know I told you your stretches are anchored on those axes. So I think that's really, really important that you stay there and handle those stretches and compressions before you start sliding. I think that'll be to your advantage. Okay? So let's just try this guy. Okay? If I strip away the parameters, do you see that essentially your parent graph is y equals absolute value of x? So you say, my starting graph is that beautiful V. And I know a few of the points on there because I know this guy really well. He's an old friend. Okay. Now, I don't care if you write these parameters down, but if it helps you, do so. My A value is -2. So you might think, what's that going to do? That's the vertical stretch, and because he's negative, flip over the x-axis. Okay? What's that 3? He's the C value, isn't he? Now, technically, because that C is subtracted, this C is a -3. And the D is a -4. Boy, we're swimming in negative signs, aren't we? Now that means that my last step will be to slide this guy. And I would slide him 3 to the left and down 4. But I want to handle the stretch first, okay? So with A being a -2, I know the 0, 0 stays put because he's anchored on the x-axis. But instead of 1, 1, I'm really going to go to 1, -2. And instead of -1, 1, I'm going to go to -1, -2. And I've got this, which I probably should have dashed. A little hard to do that now, isn't it? Okay. But you get the main idea there. And then I'm going to take that guy and I'm going to slide him and I'm going to go left 3 and I'm going to go down 4. Looks like I'm about out of space, but left 3, 1, 2, 3, down 4, 1, 2, 3, 4. Down there at the very bottom, I would have my curve and he would be opening downward. I'll tell you what, let's do this just to make my life a little bit simpler. How about if I start him right here to show you. We'll just make this my x-axis. Okay, so here was my original with the stretch. And then from there, I go left 3, 1, 2, 3, go down 4, 1, 2, 3, 4. And this would be my final graph, y equals f of x. Yeah? You good with that? Now remember, you've got 4 parameters, and you're going to want to play with them. And you might even want to go back and look at the last lesson to refresh your memory on this C and D. Okay, the C and D are just our shifts, left and right, up and down. The A and B are stretches. And again, you might want to kind of re-watch it and put it all in a nutshell and then practice. And remember, you can always double check your graph either using technology like a graphing calculator or a computer program or WinPlot, or you can use the old-fashioned way. You can make a table of values with it. Now the good news is, this is not the last time you'll see this. We'll revisit this when we get some new functions. Hey, I'll see you next time.